So the next talk will be by Brant Jones, and he will talk about a very lightweight, low-cost, compact mass spectrometer for measuring lunar volatiles. So go ahead and take it away.
All right, thank you. Yeah, forgive the title change there. I
Oh,
wrote
sorry.
that. What's that?
I can say so. He's going to talk about the Universal Lunar Mass Analyzer. Sorry, I was looking at the other sheet.
Yeah, no problem. I wrote that abstract before our Dolly submission, and I kind of changed it up a little bit. So I'm just going to give a brief overview of the instrument concept that we kind of put together in conjunction with this team. Tom Orlando, Robert Zuprin at Pioneer Astronautics, Roger Clark at PSI, and Ben at NASA Goddard. Oops, sorry, can I have next slide? So here's just a kind of an artistic render of what ALMA is really going to be doing. It's very simple. It basically has three different components: a mass spectrometer, infrared spectrometer, microwave sublimation horn, and you can kind of see from this, get an idea from this picture of what's really happening. So it's very simple. The microwaves are directed down into the regolith. The regolith then warms up, and then it releases these volatiles where they're then detected by the mass spectrometer internally and the infrared spectrometer as well. And in addition to that, we have a mass spectrometer in the exterior part of the body so that we can basically utilize this in two different modes. One we'll just call active mode with the microwave source, and in passive mode without it. So you can just kind of trace the exospheric volatiles as they're moving in and out over a typical diurnal cycle. The cool thing about the microwave source is that it actually can penetrate depths up to about 30 centimeters. This can be increased if we change the wavelength to longer wavelengths, and also increased if we were to say to put it over a drill site of, the Trident rover or something like that. May I have next slide? So I'm just going to briefly talk about the two main components of this. We chose the auto-resonant auto mass spectrometer, and it's incredibly lightweight. It's only 420 grams. It's also very robust. So it's actually operational if the length of the trap is somewhere in between D, half a D and D, which are the diameter of the end cups. So what happens is, you form these ions in this ionization region, and it has this anharmonic trap, and they just begin to oscillate back and forth, sort of like a marble would in a bowl. And then if you apply a voltage at the right frequency, then you can kind of put increase oscillation to the point, much like you would with a child on a swing, and then it gets to the point where they're actually ejected and then detected. So, you can practically drop this on the ground and it'll still work, which is not something you can say for other quadrupoles that are currently being flown. It has, fairly decent resolution, typical 100 times, which is good enough for 1 AMU. It has a pretty much theoretically infinite mass range, and this is just limited by the sweeping frequency that you put on this voltage. And we're modifying this with a cold electron source with
2 minutes left.
Yeah, which is basically a modified channel plate. So you apply a high voltage there, you generate spontaneous electrons, and then you amplify those, and you can get up to about 20 microamps with that. So the nice thing about that is that it does not outgas at all. Next slide, please. So this is the sublimation horn that Pioneer Astronautics developed with some SBIR funds last year. It consumes relatively low power, about 70 to 400 watts. So the horn actually acts as a waveguide for the microwaves and a collection vessel and a radiator as well. And so the graph in the lower right-hand corner is just showing what's happening when you increase the microwave power. So the black line is microwave power. The green is the pressure inside there. That dip in the middle is just a change in scale, so they put everything on the same scale. But you can see that as the microwave increases, the gas pressure increases. As you turn the microwave off, the gas pressure starts to diminish. And so with 1 part per billion by mass, we expect a pressure increase by about 10 to the 5 torr, minus 5 torr inside the vessel. So this will allow us to get down to parts per trillion level pretty easily. Next slide, please. So everyone, all of these bodies of text have similar objectives. That's kind of to constrain the origin of volatiles. We can do this by getting isotopic ratios, getting the binding energies, and we can also measure depth profiles as well. In addition to that, it provides can give us a way of predicting where water will go once we know the binding energies. And it also might provide a pathway to upscale microwave sublimation as an ISRU tool. Next slide. So I'll just end there. Everything has a pretty high TRL level. My partner told me that it looks like a Dalek from Doctor Who. If I had known this beforehand, I would have come up with a better acronym than ALMA. All in there. Thank you.
All right. Thank you so much, Brent.